Hi friends, in this session we will study the implementation of the PID controller. Okay. So before going to the implementation of the PID controller, let me draw our traditional negative feedback control system along with the controller. So how our negative feedback control system looks like. This is our negative feedback control system. Now in this control system, you know that is a negative feedback one, and what is the input of this control system? That is nothing but the reference input, also called as R of t, and the output of the control system is called as C of t, that is also called the controlled output. And it is a unity negative feedback, so that's why no block has been given over here. And these two blocks are, one is plant and another one is the controller. But you know, this controller block, this block in nowadays is very popularly used as a PID controller, because you know the PID controller is the best controller, right? So this is actual block of the control system along with the controller. Now you also know what is the input and the output of this PID controller or any controller. That is, this input is nothing but the error signal and output is nothing but the actuating signal. Okay, so let me write these two things also over here. So input is what? Input is the error signal, and what is the output? That is nothing but A of t, that is the actuating signal. Okay, these two signals are here. Okay, and you also know R of t and C of t. I am not going to write this over here. Now let us understand what is the main agenda over here. I have to implement the PID controller in analog domain and also in the digital domain. Now first of all, I will discuss in continuous domain, also called as a digital domain. I am writing it over here, CT domain, or CT domain or the continuous domain or the analog domain, sorry. First of all, I will discuss in CT domain or in the analog domain how this PID controller can be implemented. Now if I write the continuous time domain equation of this PID controller, including this E of t and A of t, that will be like, in continuous time, the equation of the PID controller, that is the equation of PID controller, that is what? That is the output A of t, that is equal to what? You need to know this equation very well, that is Kp into E of t plus Ki into integration of 0 to t E of t dt plus Kd into d dt of E of t. Now how this equation I have written? I have written this equation depending upon P, I and D, because this portion is nothing but the P controller, because the output is proportional to ET, A of t, or A is proportional to E. Now that's why it is called the P controller over here, or the proportional controller. Now this controller or this portion is denoted as an integral controller or I, because you can see that the output A is proportional to integration of the input E. So that's why it is called as a integral controller. and the last portion is nothing but the derivative controller, because here you see that output is proportional to d dt of e, that is the derivative of the input. Okay, so that's why the last one is the D controller or the derivative one, right? So this is the time domain equation. Whatever I have written over here, this is nothing but the time domain equation. Okay, this equation is the time domain equation of the PID controller, and I am talking about the continuous time domain equation over here. So let us, this is the very important one, you have to remember it. This is the time domain equation of the PID controller over here. Now let us first, I'm doing analysis in the continuous time domain or in the analog domain. So that's why in the analog domain or in the continuous time domain, for doing analysis we use the Laplace transform. Okay, now if I do the Laplace transform of this total equation, if I do the Laplace transform of this total equation, how this equation will look like, that is, see, this A of t will become the A of s is equal to, we will do the Laplace transform of Kp into E of t, that will be, Kp is a constant, Kp will remain Kp, and E of t will become the E of s, okay, plus Ki is also constant. I will do the Laplace transform of this integral term, that is Ki into integration of 0 to t E of t dt. So the Laplace transform of this total integration term will become, Ki will be same as the Ki, and integration of E of t dt, that will become like E of s by s, because this is the formula of the Laplace transform. You know, that is the Laplace transform, of the integration of x t dt. Okay, that is what? That is nothing but x of s into x of s by s. Okay, that is a formula of the Laplace transform. This is the important formula of the Laplace transform, you have to remember. And also another formula with the Laplace transform, that is nothing but the derivative of the Laplace transform. Laplace transform of the derivative, or d of dt into x of t, d of dt of x of t, that will become like s into x of s. Okay, so these two are the formulas of the Laplace transform. Okay, these two are the what? Formula. So I am going to use these two formulas over here. I am just using it. So Ki, Laplace transform of any constant is the same constant, that is Ki, and Laplace transform of integration of E of t, that is the E of s by s, just like as a x of s by s, and Laplace transform of this Kd, that will be same as Kd, and derivative of E of t, that is like s into x of s, and it will become s into E of s. Okay. Now if I build this transfer function, or if I take the common E of s over here, that will become like A of s by E of s. Okay, A of s by E of s, that will become like Kp. See, I have done a step jump over here. I am just taking common the E of s term from each of this term, and I am just dividing this A of s by this E of s, or the common term over here. So if I do this, that will become like A of s by E of s, that is nothing but equal to Kp plus Ki by s plus Kd into s. Okay. Now this formula is actually the continuous time domain PID controller formula, or this is the actual transfer function, okay, of the PID controller in the continuous time domain. This is what? This is nothing but the transfer function of PID controller in continuous time domains. in bracket I am writing in CT domain. Okay, in CT domain, this is the main formula of this. Depending upon this formula, I will try to, now I am done the analysis. Now I will design this PID controller depending upon this formula. Now, depending upon this formula, what is the design? What will be the design? Okay, see, if you see over here, you will learn a formula in case of the transfer function, that is A by E. That is, this transfer function is the summation of these two different transfer functions, that is Kp, Ki by S and Kd by S. Okay, this is the summation of three different transfer functions. One is Kp, another one is Ki by S, and another one is Kd into S. Okay, this is for proportional controller, this is for integral controller, and this is for derivative controller. So, addition of three different transfer functions is nothing but the parallel addition. Means which is very easy. That is what? See, there is a block whose gain is nothing but the Kp. Okay, there is a block, there is another block whose gain is Ki. Okay, and along with the Ki, you can also see that Ki into 1 by S has been multiplied over here. So that's why I am also multiplying 1 by S over here, that is 1 by S and there is another block whose gain is K of D or Kd, and along with this Kd another S has been multiplied over here, so that is the S. Now there are these three different blocks. One is Kp, second one is Ki by S, and Ki by S I have written this Ki by S separately, that is Ki into 1 by S, and Kd into S I have written this Kds separately, Kd into S. Okay, now parallel series, if these two blocks are in series, that means these two blocks, the gain of these two blocks are multiplied over here. Okay, if two blocks, that means you know this formula, if the transfer function or the gain, this formula of the block diagram representation, I think you know that, that is, if these two blocks are in series whose gain are G1 and G2, then the total gain, this total gain that can be written as G1 into G2, right? This is a formula that has come from block diagram representation. Okay, this is a rule in case of the block diagram representation. If these two blocks of having some different gains with this, if these two blocks has been compressed to a single block, then the gain of the new block will be nothing but the multiplication of these two block gains. Okay, that is whatever I have done over here, that is Ki by S. I have divided this Ki by S into two terms, one is Ki and another one is the 1 by S, and Ki and 1 by S, these two gains has been treated as two separate blocks, and I have written these two separate blocks in series. I have connected these two blocks in series. Okay, similarly Kd in S has been divided into two separate blocks, one is Kd and another one is S, and I have connected these two blocks in series, so that the total block gain will become Kds. Now these three blocks, that means Kp, Ki by S and the Kds, these three blocks has been summed over here. So if these three blocks has been summed over here, you know that another block diagram reduction formula, that is what? That is nothing but, if there is a block of G1 and another one block is G2, if these two blocks are added parallelly, okay, if these two blocks are added parallelly, two blocks having the same input over here and added parallelly, say this is x and this is y, then the total transfer function, that is y by x, that will become g1 plus g2. Okay, so this is another formula of the block diagram reduction technique in case of the control system. I think you know that. That is, if these two blocks are in the parallel, then the overall transfer function or the total transfer function can be given as the summation of these two block gains. Okay. Similarly, I have treated these three terms, three separate blocks. So that's why I am going to connect these three blocks, that is Kp and Ki by s and Kds, three blocks in parallel. So what I will do right now, I will just connect these three blocks in parallel. I will connect this with a summer. Okay. Summer, and the output of this summer will be definitely the output of this total transfer function or the total system, that is nothing but the AT. I'm sorry, here I am doing in the Laplace domain, so that's why I will write A of s, and the input will be the same, just like as this formula. The input of these three blocks will be same, and this input of these three blocks is nothing but, I'm sorry, output will be okay, just a minute. Yes, output will be A of s, right, and input will be E of s, right. Input is error and output is the actuating signal. Now, whatever I have done over here, that is the continuous time analog domain, continuous time or in the analog domain, and this block diagram or this diagram, particularly this diagram, is the implementation of this PID controller in the analog domain. Now, someone might ask me a question that if I want to implement this Kp, Ki and Kd by means of the circuits, by means of the analog circuits, then what I will do. So that's what I am going to do right now over here. That is, I am going to implement this Kp, Ki and Kd by means of analog circuits. Okay. But before that, I will just remove this formula portion over here. Okay, because I need some space. So I am just implementing these Kp, Ki and Kd. See, this is this diagram. This diagram is actual implementation of the PID controller. Okay. In continuous time domain or in the analog domain. Now, if I want to implement this Kp, Ki and Kd by means of some analog circuits, now what I will do, right? This is my questions, my agenda. Now, which is very easy, that is for Kp, I am just going to analog circuit implementation. Now I will implement these three things, Kp, Ki and Kd by means of analog circuits, that is nothing but via op amp. Why op amp? Now see, in case of the proportional controller, if I try to implement the only proportional controller means I am trying to implement that Kp. Okay, I am trying to implement the Kp. Then what will be the circuit? Circuit will be like this. Okay, and this will be definitely the error E of t, and this is nothing but the A of t. Now why the circuit will be like this? See, if you remember this circuit, then the gain of this circuit, this is nothing but a circuit of the op-amp operational amplifier along with the negative feedback. Now you know what is the gain of the negative feedback closed loop operational amplifier. That is nothing but A of S by C of S. See, I am going to write this in the S domain. Okay. So now don't become confused that I have written over E of t. Sir, you have written here E of S. Now I have written A of S and E of S means I have just doing the Laplace transform of AT, that is the A of S, and I have done the Laplace transform of ET, that is the E of S. And you know that the Laplace transform of R1 and R2, that is nothing but the resistance and resistance values are constant. Now the Laplace transform of R1 and R2 will be same, that is R1 and R2 just as previous as it was. Okay, there will be no change in the R1 and R2 configuration in case of the Laplace transform, because the Laplace transform of any constant is nothing but the same constant, right? So A of S by E of S, that is nothing but the gain of a closed loop operational amplifier in the negative feedback. That is nothing but, you know, that is nothing but the R2 by R1. Okay, you know this formula. Now see this term very carefully. R2 by R1. See, R2 is constant, R2 is constant, R1 is also constant. So this total term is constant. This total term is constant, and you know that Kp is also a term which is constant. So that's why this total term is written as the Kp. Okay. So the configuration or the gain formula of this configuration is looks like constant, which is nothing but the Kp, because you know that in case of the proportional controller, Kp is also constant. Okay, in case of the proportional controller, Kp is a constant, right? Or you can say like that, this is a proportional controller, what will be the constant of the proportional controller? That is nothing but the Kp. Okay, so this circuit, the circuit I have drawn over in the left side, that is the implementation of this Kp. Okay, now let me implement the integral one. Now in case of the integral controller, you know that in case of the integral controller, the proportionality has been replaced by this term Ki by S. The proportionality has been replaced by the term Ki by S. So I have to design some circuit like that. One more thing, that is nothing but Ki by S means what? Ki is nothing but the constant. So some constant by S. So I have to design the analog circuit, a new analog circuit like that, whose gain will be the form of some constant by S, whose gain will be, here the gain has been formed in some constants that looks similar like this Kp. Okay, but in case of the integral controller, this proportionality has been replaced by the Ki by S, where Ki is nothing but a constant. So I have to draw a circuit such that whose overall gain will look like some constant by S. Okay, so how this circuit will look like, let me show you. Again I will use the operational amplifier. Along with the negative feedback, but the feedback path has been replaced by a capacitor, not the resistors. Okay, now this circuit is also known to you. Why? This circuit is also known to you. In analog electronics, you have read about the RC integrator circuit. Now this circuit is nothing but a RC integrator circuit. Okay, this circuit is nothing but the RC integrated circuit. Why I have chosen the RC integrated circuit? Because I am going to implement the integral controller first. Okay, I am going to implement the integral controller, that's why I have chosen the RC integrated circuit, because the gain of this integrated circuit, okay, this gain of the integrated circuit means A of S by E of S. This gain of the integrated circuits, okay, that is nothing but, or you can also say like that, one more thing, but before doing that you have to just do the Laplace transform just like as previous. So E of t can be represented at E of S, and A of t can be represented as A of S. So R is a resistance which is a constant term, so Laplace transform of any constant is nothing but the R. But in case of C is represented by 1 by Cs in case of the Laplace. Okay. So now if I try to determine the gain of this circuit, that is the A of S by E of S, that is A of S by E of S, just like as previous, I am trying to determine the gain of this. So A of S by E of S, that will look like, if you do the derivations, that will nothing but 1 by Cs, just like as this minus R2 upon R1, that is minus of feedback resistance by the forward resistance. Here will be minus of feedback impedance. Feedback impedance is nothing but the 1 by Cs by forward impedance. So you can, it is a formula. See, whatever I have told you, that is A of S by E of S, that is nothing but the minus of feedback impedance by the forward impedance. Feedback impedance by the forward impedance, this is the formula. Minus of feedback impedance by the forward impedance, this is the formula for what? This is nothing but the formula for negative feedback closed loop operational amplifier. Okay. So if I substitute this numerator over denominator, that will nothing but the 1 by RCS. Okay. So if you do this, this is now this thing is nothing but now our what? This is nothing but the total gain of this integrated circuit. Now if you look at this gain, this term properly, okay, you will see that this term looks like Ki by S, because this term can be written as minus of 1 by RC, where R and C both are constant. So minus of some constant means that is nothing but some constant divided by S. That means this is nothing but what? This is nothing but some constant by S. This term is the same term whatever I require to design a PID controller, that is Ki by S, because that is nothing but, I can write Ki by S, because you see over here that the term or the gain has been appeared over here, that is nothing but some constant by S. Now some constant by S is nothing but equivalent to Ki by S, because Ki is also a constant. Okay, so what is the value of Ki over here? I am also writing over here, that is Ki is nothing but minus 1 by RC. Okay, Ki is nothing but the 1 by RC. Kp is what? Kp is minus R1 by R2. Remember these values. Okay. Now you see that Pi, that I have drawn the circuit, or I have drawn the analog circuit of P and I. So let me draw the another circuit, that is the D, in case of the derivative controller. So I am removing these things. Okay. So I am removing these things. So let me draw the circuit of the derivative controller. Now you know, in case of the derivative controller, the proportionality, that means this proportionality, has been replaced by KDS. Now you know that KD is constant, so I can write it like some constant into S. Okay. So I have to draw the new analog circuit in such way that the total gain of that analog circuit will become some constant into S. Okay, some constant into S, right? So in the similar way, I will use definitely the operational amplifier. So let me use an operational amplifier, and obviously in the negative feedback. Okay, so I am using the operational amplifier over here along with the negative feedback, and the input of the operational amplifier is what? Input of the operational amplifier is nothing but the error signal, and output is nothing but the actuating signal. Okay, and the feedback path has been replaced by the R, and the forward path has been replaced by the C. See, whatever I am going to do over here, tell me, whatever I am going to do over here, I am going to design a derivative controller, only the derivative controller. See, why I am trying to design the P, I and D separately, I will make you understand it later. But for now, just listen to me that in case of the derivative, in case of the integral controller, I have used the integrator circuit. So definitely in case of the derivative controller, I will use the derivative circuit, or the here RC integrator I have used, here I will use the derivative circuit. Okay, this is nothing but a derivative circuit. RC differentiator, this is called. See, if you remember this circuit, in case of the operational amplifier, we studied that this circuit acts like a differentiation. This circuit is nothing but the RC differentiator. Okay, so if you are facing some trouble to remember these all three circuits, I will make you understand very carefully. See, in case of the proportional controller, both feedback path and the forward path is nothing but the resistance only. In case of the integrator, see, if I talk about the integrator, then the RC integrator term, the listen to my pronunciation carefully. RC integrator terms. RC integrator means first in the forward path it will be R, then it will be C, not the reverse. RC, you are pronouncing RC, that means R, in the first I will write R, then I will write C, not in the first I will write C, then R. First R, then it will be C, RC integrator. Now, in case of the differentiator circuit, this integrator circuit will be reversed. Reversed means the C will be positioned in the forward path and the R will be positioned in the feedback path. So whatever I have writing, that's whatever I have drawn over here. That in case of the feedback path, I have put the resistance R, and in case of the forward path, I have put the capacitor C. This diagram and this diagram, these two diagrams are exactly opposite to each other, because this is a differentiator and this is an integrator, and differentiation and integration are opposite to each other. Okay, so right now I will try to check the gain of this circuit, so that let us see that gain becomes some constant into S or not. So for that I have to do the Laplace transform. E of t will be nothing but the E of S, and A of t will be nothing but the A of S. Okay, R will be R because R is a constant, and C will be 1 by Cs. Okay, now as in the previous formula I have told you, this is nothing but the negative feedback operational amplifier. So what will be the gain? Gain will be nothing but A of S by C of S, obviously the output by input, and that will be nothing but equal to minus of feedback path. In the feedback path, whatever I have drawn over here, that is the R. So just writing R, minus of feedback path impedance by the forward path impedance. Whatever is the forward path impedance? Forward path impedance is nothing but the C. In the Laplace, I have written over 1 by Cs. Okay, so if I write these total things over here, that will become minus RCS. Okay, so this is our total gain in case of the, this is our total gain in case of this derivative circuit. Now if you look this gain carefully, okay, if you look this gain carefully, this gain is nothing but minus RC into S, because you know that R and C both are constant, so that means this is nothing but some constant into S that can be written as KD into S, that is similar like KD into S. So I have designed some circuit over here so that its gain has become some constant into S form. That means that constant is nothing but minus RC into S. So from here I can easily write what is the value of KD. KD is nothing but the minus of RC. Okay, minus of RC. Now for now I have designed, right now I have designed the three things. See, right now I have designed the three things. Okay, whatever I have designed the P, proportional, integral and derivative controller separately by using some analog circuits. Now you know this diagram, whatever I have drawn the past, this is actual implementation of the PID controller in case of the continuous time domain. But if I represent this diagram in the form of circuit, okay, then what this diagram will be? This diagram is nothing but, you can see that first which is very easy. I will just replace these three circuits in case of the Kp, Ki by S and Kd into S, right? Then this diagram will become the analog circuit diagram. Okay, that means whatever I will do, see here this proportional circuit, the gain of this proportional circuit is Kp. So in case of this Kp, I can replace this Kp by this operational amplifier circuit, okay. Similarly, the gain of this integrator circuit is nothing but the Ki by S, okay. So that's why I can replace this Ki by S term by using this operational amplifier circuit, okay. Similarly, in case of this derivative circuit, the gain of this derivative circuit is nothing but the minus RC into S, or that looks like KD into S. So I can replace this KDS by this circuit, this operational amplifier circuit. That's whatever I am going to do over here. So for that I have to remove these things also. Okay. So I am implementing the analog circuit. Okay. First of all, in case of the Kp, I will draw this circuit, right? So just draw this circuit. Okay. Now I will write the input output later, but yeah, this circuit I have drawn over here. Now in case of the Ki by S, I think you remember the previous diagram, whatever diagram I have drawn just right over here, okay. So in case of the Ki by S, whatever I will draw this circuit. This circuit is nothing but the RC integrator. Okay. And in case of the just a minute, just give some space. Okay. Okay, this is nothing but the RC integrator, and in case of the KD into S, I will draw this circuit, that is RC differentiator. Now these three circuits, okay. Now what I will do now, I will join these three outputs just like as in the previous diagram. I will join these three outputs, and the final output will be what? Output will be nothing but the actuating signal, and the input of these three circuits is same, and that input is nothing but the error signal. Now I think you can understand these three things, because this is this circuit, the last one. What this circuit is actually, this is nothing but the this circuit is what? This is nothing but the KD into S. Okay, because this is the RC differentiator, right? What is the middle one? Middle one is nothing but the RC integrator. Okay, that is the KI by S. That is what? That is RC integrator. And the what is first one? The gain of the first one is nothing but the what? KP. The gain of the first one is what? That is nothing but the KP. Okay. So KP, KI by S and KD by S. Our PID controller has been designed. Our PID controller has been designed in case of the continuous time domain or in the analog domain by using the operational amplifier over here. That is our implementation of the PID controller in case of the analog domain. Now I will discuss this implementation of the PID controller in case of the digital domain. Now to design the PID controller in the digital domain, so let me write the generic PID expressions in case of the continuous time domain. So in case of the CT domain, you know the expression is what? The actuating signal, that is nothing but KT into E of t plus KI into integration of 0 to t E of t dt plus KD into derivative of E of t. Now, in case of the discrete, see, from continuous to discrete, what I do? In case of the continuous to discrete, I just do the sampling. Sampling means I represent this t to nts, where n can be any value. That means nothing but I have done the sampling. I have done the sampling with the time interval of the ts. Okay. Now this thing is not so important. What sampling I have done, how much sampling I have done, this thing is not so important. But the important is the sampling, whatever I have done in the continuous time signal in the I have done the sampling on this continuous time signal to get the discrete time domain equation, and the sampling time interval is nothing but the ts. Okay. Why I am telling you like that? Because in case of the discrete domain, you know, we write A of n, and the Kp is nothing but the Kp into E of t can be written as the E of n, because in case of the discrete domain, we represent discrete time domain. Definitely in case of the discrete time domain, we don't use the t, we use 10. We use n. Okay. Plus, see, the integration in the time domain. Remember these things. Okay. The integration in the time domain, as just a minute, I will write it like A of n equal to Kp into E of n. Now I am writing this discrete time domain equation, remembering this continuous time domain equation only. Now, in case of the continuous time domain, if the integration occurs, the discrete time domain, the integration will behave like a summation. Okay, this is a formula. And also in case of the continuous time domain, is derivative, if derivative occurs in discrete time domain, I can represent this derivative as a difference. Okay, I can represent this derivative as a difference. This is the two formulas. Okay, This is nothing but the two formulas. Okay, you have to remember it. So the constant term I will write the constant term as it is. Now wait a minute. I will write this integration of E of t. Listen to each and every words. I will write this integration of E of t in by means of the summation. Okay, and in case of the integrator, just one thing you have to remember, as I have done the sampling by means of TS, this TS time will be introduced over here. So Ki will be represented as Ki into Ts. In case of the discrete time, in case of the continuous time domain, it was Ki. In case of the discrete time domain, I will write Ki into Ts, and the integration will be changed as the summation. Okay, summation of E of k, where this k will be varied, just like as here it was varied from 0 to t, here it will vary from 0 to n, because in case of the discrete time domain we replace t by n. So that's why 0 to t has been replaced by 0 to n, and I have taken some dummy variable k, so that we can vary this variable from 0 to n. Okay, so that means our summation, that means this integration has been represented by this summation. Okay, remember this. Now similarly, okay, just remove this. Okay, this is a formula. And similarly, the derivation or the derivative in case of the continuous time domain, the derivative is represented by what? Derivative is represented by the difference. Okay, so but here one thing you have to remember, in case of the integrator, the Ki was represented by Ki into Ts. In case of the derivative, the Kd will be represented by Kd by Ts. Okay, Kd by Ts. Okay, here the Ts was multiplied with Ki, here the Ts will be divided, here the Ts will be divided. Okay, so the derivative in case of the continuous time domain is represented by the difference. So how the difference will be written? That is nothing but the E of n minus E of n minus 1. E of n minus E of n minus 1 means that means it is nothing but I am taking differences of two consecutive sequence. Okay, I am taking the differences of two consecutive sequence of E of n. Okay, E of n and E of n minus 1 means if this is a 0, this is a 1, if this is a sequence like this, that means I am taking the differences. If this is a E of n, that means you can put the n equal to 0 over here. That means I am taking the differences of E of 0 and E of minus 1. Okay, or you can put here E of 1 also. E of here, if you put n equal to 1, so that will be like E of 1 and E of 0. That means I am taking the differences of these two consecutive sequence. I am taking differences of these two consecutive sequences. Okay, so it was just for understanding, but the main thing is nothing but the derivative or the differentiation has been written in the form of difference. Okay, so differentiation, here integration has been written by summation, or here differentiation has been written by the difference. Okay, and the differentiation has been written by the difference if I move from continuous time domain to discrete time domain. So whatever equation I have written over here, this equation is very much important. This equation is nothing but the equation of the PID controller in case of the discrete time domain. This is nothing but the equation of PID in discrete time domain. Okay, now in case of the continuous time domain, we did the Laplace transform. Similarly, for discrete time domain analysis, we will do Z transform. Okay, So if I do the Z transform of this total sequence or this total equation, how this equation will look like, and depending upon it I will do the design. So A of n, the Z transform of A of n can be written as A of Z, you know. Now Kp, the Z transform of any constant, is the same constant over here, and E of n will be represented by E of Z, you know. Now Ki into Ts, that is again a constant, so Ki into Ts will be written as it is. Now the summation of Ek, remember this point, there is a formula in case of the Z transform, so Z transform formula I am writing. The summation of x of n, okay, or x of k, which is varying from k0 to n, that can be written as, okay, the summation can be written as x of z by 1 minus z to the power minus 1. This is one formula. Okay, I am writing it freshly, just a minute. So summation of k0 to n, okay, x of k is z transform of this signal, that will be nothing but x of k, for x of k it will be x of z and 1 minus z inverse. That is the formula for summation. Similarly, the z transform of difference can also be given like this, x of n minus 1. If I do the z transform of this signal, then that will be nothing but 1 minus z inverse into x of z. So these two things are the formula you have to remember in case of the z transform. I think you remember it, the formula for the summation and the formula for the difference. So what will be this signal? This signal is nothing but A of z, that will be equal to Kp into E of z plus Ki into Ts, that is a constant. Now summation of E of k, that is nothing but the E of z. Here summation of x of k was x of z by 1 minus z inverse, so that will be nothing but the E of z by 1 minus z inverse, okay, plus the Kd by s, okay, plus the Kd by s into the difference E of n minus E of n minus 1. Similarly, this x of n minus x of n minus 1, that was the z transform of this signal was 1 minus z inverse into x of z. Similarly, I can write 1 minus z inverse into what? E of z, okay. Now if I take this E of z term common from this right hand side and divided this E of z in the left hand side, that is E of z by E of z, okay, then it will become like Kp plus Ki Ki into Ts by 1 minus z inverse plus 1 minus z inverse into Kd by Ts, okay. Now this is the transfer function, whatever I have written over here, this thing is nothing but the transfer function of PID controller, but I have done the Z transform over here, right? So that is in PID controller in discrete time domain. Again remember, in case of the continuous time domain I did the Laplace transform, in case of the discrete time domain I have done the Z transform. So one more thing that you may forget, that in case of the continuous time domain equation it was integration, in case of the discrete time domain equation it is summation, in case of the continuous time equation it was the derivative, and in case of the discrete time domain equation it is the difference, okay. So this is the function, or this is the transfer function of the PID controller in case of the discrete time domain. So now depending upon these functions, depending upon this transfer function, I will try to draw this controller in case of the discrete time domain, okay. Now how I will draw it? Now drawing the controller in the discrete time domain or in the digital domain, that is implementation implementation in digital domain. How I will draw it? Just like as previous. See, this transfer function is the summation of three different transfer function. One is Kp, another one is Ki into Ts by 1 minus Z inverse, another one is 1 minus Z inverse into Kd by Ts. Okay. So, as the summation of the three transfer function means the three transfer functions of the three blocks will be parallel to each other. Just in previous I have shown the rule of the block diagram representation. In case of the block diagram representation, you have seen there are two rules. If two blocks are in series, then the overall gain of these two blocks of this circuit will be nothing but the multiplication of the gains of these individuals. Okay. But if these two blocks, if the two blocks are in parallel or connected parallelly, then the overall gain will be nothing but the summation of the gains of the individual blocks. Okay. Similarly, just like as in case of the previous circuit, I will try to design the new circuit in the similar way, just like as previous. That is what? First of all, I will draw this one. That is Kp. Kp is single, written over here. Kp is nothing but a gain. So I have put a gain. See, this triangle block represents, this is a gain. Okay. Now, one block has been drawn over here. The second block is Ki into Ts by 1 minus Z inverse. So, first of all, I am dividing these things into two parts. Just like as in case of the Ki by S, I divided that into Ki into 1 by S. In the similar way, I am dividing this thing Ki Ts by 1 minus Z inverse into Ki Ts into 1 by 1 minus Z inverse. That means I am taking this Ki Ts in one gain Okay. Now coming back to this term 1 minus z inverse. Now see, the transfer function of 1 by 1 minus z inverse, that can be written, that can be drawn like this. How? Which is very easy. Just like this. Now you may ask me a question, how this can happen. You can determine the overall transfer function over here. I think you can do it. How? Because this is a GS, GS is nothing but 1, GS by 1 plus, in case of the negative feedback, I am sorry, it will be the positive feedback, GS by 1 minus GS into HS, here GS is 1. So do this 1 by 1 minus GS into HS means 1 into Z inverse. So this overall transfer function will become like this. That means I am just writing out over here, so like okay. The gain of this, overall gain of this circuit will be like what? GS by 1 minus GS into HS. In case of the positive feedback, I do this GS by 1 minus GS into HS. GS is nothing but the 1 by 1 minus GS into HS means HS is nothing but the Z inverse. 1 into Z inverse means Z inverse. Okay. This thing you have to remember. And another one thing that you have to remember, that is nothing but this, which is easier one. This is easier one. That is, if you try to write the overall transfer function of this circuit, that is nothing but, what is this? This is nothing but 1, because 1 is added over here, 1 is added over here, minus of Z inverse. Okay, minus of Z inverse, right? So This block is nothing but the 1 minus Z inverse. Why? Again I am telling you that 1 is directly adding with this forward path, and along with that there is another part of the Z inverse block. So that means along with the 1 I am subtracting the Z inverse. Along with this 1 I am subtracting the Z inverse. Okay, this is a 1 was going as it is in this direction. Okay, and in this direction the Z inverse block has been subtracted. So that's why I have written 1 minus Z inverse. See, these two things are nothing but the basics. Okay, why I have written this over here, because you will understand that along with the Ki into Ts there is a multiplication of 1 by 1 minus Z inverse, right? So what I will do right now, along with the Ki into Ts I will draw this circuit over here. That means okay, now this circuit is nothing but 1 by 1 minus Z inverse. This circuit is nothing but 1 by 1 minus Z inverse into Ki into Ts. So this term has been completed. Now the third one, the last term, that is nothing but Kd by S. So I will write this Kd by Ts into one block. Now the triangular block represents the gain, and along with that I have multiplied 1 minus Z inverse. Now 1 minus Z inverse circuit can be represented like this. So I can draw this circuit like this. The one there is nothing is mentioned, means this gain is nothing but the 1. So this is added, and 1 minus Z inverse means Z inverse block. See, this Z inverse block has been subtracted. That's why I am giving it the minus sign over here. Okay, so this block is nothing but the 1 minus Z inverse. Okay, so the three blocks has been represented over here: Kp, Ki into Ts by 1 minus Z inverse, 1 minus Z inverse into Kd by Ts. The three blocks has been represented parallelly. Now for addition, what I will do just nothing but the parallel connection. So for the parallel connection, what I have to do? I have to do the I have to give the same input over here. That same input is nothing but the E of n, as I am in the discrete domain, and that's why I have written n, not t. Okay, and here the summer will be over here. Three signals will be summed up. Okay, three signals will be summed up, and the output of this will be nothing but the actuating signal, that is nothing but the A of n. Just a minute. Okay, where this signal, two things I want to mention over here, that is this block is what? This block is what? This block is nothing but the Kd by Ts into 1 minus Z inverse. This block is what? Ki into Ts by 1 minus Z inverse, and this is the Kp you can directly see over here. That means P, I and D has been implemented in the discrete domain. So this is the final implementation of the PID controller in case of the discrete domain. Okay, that's all about it. But remember, don't forget these two things. This configuration, this small configuration represents the 1 by 1 minus Z inverse, whatever I have, I drew it over here. and this small circuit, that is the gain of this circuit is nothing but the 1 minus Z inverse, that whatever I have I drew it over here. Okay, so this is the total representation. This is the in case of the digital domain. Okay, thank you.